Okay. Puedes ver el slide. ¿Sí?
Sí, sí.
Muy bien. Entonces, estuvimos hablando acerca de este Monte Carlo Estimator. Y la idea era estimar este θ, ¿no? Θ como el expected value de esta función h of x, donde este x es un vector de random variables. ¿Ok? Es un vector que está aquí en Rn. Entonces, Monte Carlo dice, nos permite estimar este θ como θ hat n como tu sample mean. El sample mean de esta función aplicada a unas xi, donde estas xi, ¿no? Conforman una cosa que se le llama random sample, ¿no? Que es un conjunto de random variables, bueno, en este caso random vectors, que son IID. Es decir, todos provienen de la misma distribución y se han sampleado de manera independiente. Luego, sabemos que el Strong Law of Large Numbers nos dice que θ hat n, es decir, nuestro Monte Carlo Estimator, converge in probability to the true θ. Then, two questions arise. The first one is, how large should n be set to have a confidence that our Monte Carlo estimator, θ hat n, is a good estimator of our true value θ? This must be like 10,000, 100,000, 1 million. A priori, we don't know. And the second question is, for a fixed n, once we fix the value of the sample size, what can we say about the quality of our Monte Carlo estimator, θ hat? Okay. Here we need to define what is quality for us. Okay. I think we have talked a little bit about the quality of θ hat n. For that, we need to define confidence interval. We have done that our last lecture, so we will not talk about this. Even this, we talk about the central limit theorem and how the central limit theorem will can help us to construct confidence intervals for our Monte Carlo estimator, or for the true value using our Monte Carlo estimator. And because we don't know the variance of our of these guys, h of xi, we estimate the variance using the sample variance. Okay, so we replace the true value of the standard deviation of y by the the standard the sample standard deviation. Okay. Then we have our confidence interval. Now, the quality the quality of the estimator will be the half distance between the limits in the interval. Okay, the half distance. That's the quality of the estimator. For example, in this case, what is the quality of the estimator? It's the half size of the interval. So this guy minus this guy over 2. Minelli? Buenas, buenas. Ahí.
I'm here, but I don't know.
Okay. As I said, the quality is just half of the size of the interval. For example, if the interval were like 1,2 close interval, the quality is just 1/2 because it's 2 minus 1 over 2. Okay, if the interval were 0,5, the quality will be like 2.5. 5 minus 0 over 2. In this case, what is the quality of the confidence interval?
Teacher, the first part of the interval.
First part of the interval. What do you mean? With the first part? Give me a second. Can you hear me? Okay. Interval or confidence interval? Is theta hat n minus sigma hat n for square root of n times c1 minus alpha half theta hat n minus that over square root of n. Okay, that is the confidence interval. So the quality is
Ahí consumo.
sorry, did I miss something? Okay, should be plus. Okay. And then the quality would be half the distance, or half width. It's called theta hat plus or square root of n times minus half alpha minus beta hat hat n square root of n times what is that? Now the quality will be okay, and it's half of this. Then it will be over square root of n. This is one measure of quality. Okay. This is one way of measuring the quality of the Monte Carlo estimator. So estimate. Okay. So the quality improves when this guy goes to 0. So in which way we can make that this guy go to 0? Making, there are two ways. Making n row infinity, or what is the other way?
Desviación estándar nula, pero
Make this guy go to 0. So in this lecture, we're going to talk about this. Because the first question was, how large should we set or fix n? Then, once you fix n, what can we talk about the quality of our estimator? Okay, this is lecture. Today's lecture. Here is the topic that you need to revise if you want to learn more about how to improve the quality of the Monte Carlo estimator. Is called variance reduction. Okay. We can talk about this, but in a slightly way. Okay. So now, let's know what is the quality, or how can we define the quality? Let's see how to fix n. Okay, so let's go back to the slides. There is something that we call run length control. Okay, we need to find a way to fix the size of our sample, random sample. Okay, there is some criterion. We're going to talk about the error criterion. So to talk about the error criterion, we need to define first what is an error. So there are two ways of defining error. The absolute error, which is the distance between the Monte Carlo estimator or any estimator and the true estimator. Okay, that is the absolute error. And the other error is the relative error, which is the absolute error as a percentage of the true value, both in absolute values, okay? So what happens when n goes to infinity? The error will go to 0, okay? But we know that n will never be infinity, so we expect to have errors that are different from 0. So now, let's say we fix alpha, a number between 0 and 1, and we fix also epsilon, a positive or non-negative number. And let's say we want to set the probability of making a mistake, that making a mistake is not larger than epsilon. And we set that probability to 1 minus alpha. Okay? So first we set the probability of making a mistake. So the probability of making a mistake is alpha. Or in other words, the probability of bounding our error by an epsilon will be 1 minus alpha. It's like our confidence interval, something like that. So if we do that, and because there is a property about our estimator related to the CLT, we know that the absolute error will be less than equal than the half width of the confidence interval, right? Are you with me with this property? And this must be like approximately 1 minus alpha.
Teacher, will you mind explaining the first part again, please?
Which one? This one or this one? What do you mean this one?
Yeah, no, the first part that is in the box, please.
Ah, okay, okay. Okay. Okay, there are two errors. The absolute and the relative. This is theta hat n minus theta. Okay. So what I want to do is bound the error. Okay, the mistake. This is the error. I don't want the error be larger than some epsilon. Okay, let's say I'm trying to compute the value of an American Asian option. Okay, and I want that the error of making that price be less than 0.1 or less than 50 cents. Okay, that is something that I want to do. I want to bound the error. I know that I will make an error because this way of estimating, for example, the price of an option is a stochastic method. So there will always be an error. But what I want to do is just bound that error. I don't want the error be large. And I don't want to feel that I'm making less money that I can do. So I bound the error by some epsilon. I set this number. This is something that I will fix. And I want to set this probability to 1 minus alpha, where this guy is also fixed by me. So these guys are your like control variables. Let's say you fix alpha to 5%. So the probability that the error is always less than some epsilon, let's say. This is 95%. Only 5% of the times you will have an error that is greater than 0.1. So that is the idea behind this formula.
Teacher, in the last part, for example, in the O.1, this number has a specific measure. It can be, for example, I don't know, dollars, soles, something like that, or it's only a number.
For example, if theta n, theta hat n is the price, this is the price of an option, this is dollars. Because this is dollars, this is dollars. When we are talking about the absolute error. If we talk about the relative error, we are talking about just the percentage. It's like, okay, the error, this is relative, less than, let's say, 1%. 1% of what? Of the true value. That is your bound. 95%. So when you use the absolute error, this could be dollars. If you're trying to estimate the value of an option, the value at risk, those are dollars. Soles.
Okay, thanks.
Excellent. Then, okay. For example, do you remember this kind of problems? If you want to remove the absolute value, what would you get?
El X entre el venezolano y el no.
Good. What about here? What about here? What would you get? Ricardo? Yori?
I think it would be between -1 plus theta is
Theta
-1.
-1. Here,
1 plus theta.
theta
Oh.
plus 1.
Yeah.
Okay. What about this guy? Example number 3. Diego Alonso, what do you think about this? What would you get? You remove the absolute value.
I think that maybe theta estimates in the middle is between the part that is on the right plus the true value of theta, and the other part, also the part is on the right plus the true value of theta.
Okay. Let's say no. So I want to solve for theta true, the true theta, not theta hat. It should be the same, right? Because this is absolute value. Solve for theta, not for theta hat m. So theta should be between minus plus. Here you put theta hat, right? Hat. Now, if you see this guy and this guy, can you relate those guys? Yes or not?
Is the same interval like in a confidence interval?
So, what will be the proof? probability that theta had n minus theta, that this guy will be less than what is this probability? When n goes to infinity.
One minus alpha.
1 minus alpha. Since this guy would never be infinity, then this is not equal, but approximately. And who is this guy?
The absolute error.
The absolute error. So you see, we're saying that the absolute error, if we set epsilon, this is our epsilon, to this guy, then the probability of the absolute error be less than this guy would be approximately 1 minus alpha. So we are setting epsilon this guy minus alpha. Can you solve for n? What is the value of n? Can anyone tell me? Vania?
Se tiene que despejar n en este caso. O sea, sería n es igual a, bueno, ya todo eso entre la e al cuadrado, todo.
Right? Because this is a square root of n. So we need to square the whole expression, the right and the left hand side of the equation, then the rest, you know, it's just algebra. Okay, so this is one way of fixing the value of the size of your Monte Carlo simulation. Okay, so once you fix this guy, say this is 5%, your absolute error bound, let's say, is 0.1. Let's say you know who is this guy, 20%. Then you just need to replace all these guys here, and you will get what is the size of n. And that's it. Any question? Or do you think that there is something that looks like fishy? at the CBU. Here there is something that you don't know. What you don't know if you want to compute n using this formula. So alpha, you say. Epsilon, you say. But this guy is unknown for you. Because if you want to compute or estimate sigma hat, you need to set the value of n. But we need n, we need sigma hat to set the value of n. Right? Are you with me with this expression or with this fact? We don't know theta. Sorry, sigma. Even the estimator. We don't know the true value of sigma, and we don't know the estimator of sigma, because if you want to compute the estimator of sigma, you need to fix the value of n, but we are trying to do this to fix the value of n. So what will be first, n or sigma? Let's go back to the slides. What also will happen with the relative error? Look at this.
En este caso, como no sabemos el valor de sigma, asumimos cosas, ¿no? O sea, asumimos un sigma promedio, ¿sí? Para hallar el n.
Buena pregunta. So this is for the absolute error, and this is for the relative error. I will answer the question next slide. Okay. There are some issues that can arise. First, controlling for the relative error, you need to know the true value of theta and also the true value of sigma. And for controlling, if you want to control for the absolute error, you need to know sigma in advance. We don't know those guys. Actually, when you want to control by the relative error, you need to know the true value, but you want to estimate the true value. So this is worse than this. So two ways of dealing with these two issues. First, let's say you want to control for the absolute error, then you will do two simulations. Okay, first, a pilot simulation to estimate sigma square, and once you know sigma, you will put sigma here, then you get n, and once you get n, you will do a new main simulation and estimate theta, and construct a confidence interval for theta. Okay, that method is called the two-stage procedure. Okay, there are two ways of doing this. One is the two-stage procedure. The algorithm of the two-stage procedure follows like this. First, you run a pilot simulation, generate the x, estimate theta hat, then sigma hat. You plug this sigma hat in the formula, then you set n. once you set n, you generate another set of random variables, random vectors. You can see that n here, this guy is here. So the size of this main simulation have been found here in the pilot simulation. Then you just estimate theta, sigma, then you construct the confidence interval for theta, for the true value of theta. And that's it. Then the question is, what is the size of our first pilot simulation? It should be sufficiently large, greater than 50. You can put 100 or 1000. Let's say 1000. It's okay. So between 100 and 1000, you will do your first simulation to compute n. Once you get n, then just continue with the main simulation. And this story is already known by you. Questions? Vania? Gabriel?
It's everything clear.
Everything clear.
Yoli? Pro you?
Todo bien, profe. Solo, ya para que me quede súper claro, el pilot tiene que ser mayor a 50, ¿no? Esa es la condición.
Así es.
Ok. Todo claro.
Los demás. Entonces vamos al break. Si no. Y regresamos y hacemos un ejemplo en R. ¿Qué opinan?
Ya, perfecto, profe.
Sí, está bien, profe.
¿Les gusta la idea? Así
Está
como que
bien,
lo,
profe.
como que lo ven en... Perfecto. Listo, chicos. Entonces, 8:40. Hola chicos. Al estudio. Pueden ver la R y los slides.
Sí, profe.
Sí, profe.
Muy bien. Entonces, ya. ¿Qué quieren estimar?
Profe, ¿podría ser el mismo ejemplo que hicimos con el uniforme, el integral de 1 a 3 de x al cubo?
Perfecto. Era esto, ¿no?
Ah, sí, 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 eso.
Entonces, aquí nos dimos cuenta que esto es 2 times expected value of x. Oops. Ok. Entonces, primero, pilot simulation. Pilot simulation. Then we need to generate our x. And if okay, and we compute what is this y. I will be x squared. Then compute theta pilot. And sigma e will be standard deviation of y. Finally, n will be of times over epsilon. We need to fix
Bueno, me parece que es 2x, 2 esperanza de x al cuadrado. En la fila 2.
right? Right, 2 times the mean. Or the way is like this. We need to fix epsilon. Okay, this is 0.1. And alpha. Let's say this is 0.5, which means Q norm that is the size of n. See? So first you need to fix epsilon and alpha. With alpha, you will compute C. This is 1.95, 96. Almost. Then you run your pilot simulation. You set the size of the pilot simulation 100. This is for me. Then you simulate X. You compute Y as 2 times X squared. Right? Then compute theta hat for the pilot simulation, sigma hat for the pilot simulation, and finally you estimate n using this formula. Okay, here is square. Also here is square. Here is square. This is the size actually. Then, so far, any question about how to compute n in the pilot simulation?
Everything fine, teacher.
Then you run your main simulation. So instead of P, use n, but you need to enter into a figure. And the rest is okay. Then the confidence interval will be minus C times sigma over square root of n plus. Do you remember what is the true value of the integral between 1 and 3 of x squared?
Preguntitas.
Profe, yo tengo una pregunta. Me acuerdo que cuando hicimos Monte Carlo, en un ejemplo, o sea, o sea, hicimos solamente, corrimos prácticamente la segunda parte con un número n muy grande. Entonces, tengo dos preguntas. En primer lugar, ¿cuándo sería necesario hacer como el pilot simulation? Y la segunda es, ¿cuándo sí se podría evitar para no hacerlo?
Ok, voy a responder la pregunta. O sea, si ustedes hacen su Monte Carlo Simulation, ustedes dicen, oye, pero esto es fácil, profe, ¿no? Porque yo le puedo poner 1.000.000, 100.000, y todos bien, todos contentos. Sin embargo, en la vida real, ya, este tipo de simulaciones, por ejemplo, para riesgos o para valorización de portafolios, por ejemplo, cálculo de VaR, ¿ya? O cálculo de VaR, cálculo de CVA. ¿Han visto counterparty risk? ¿Alguno ha visto eso? Es parte del credit risk, pero es credit risk de derivados. Y entonces, calcular el CVA, ¿ya?, de un portafolio toma mucho tiempo, porque tienes que hacer muchas simulaciones, hacer valorizaciones en el tiempo. Entonces, no es tan sencillo como fijar N en 1.000.000, porque no vas a terminar de hacerlo, eso toma mucho tiempo. Por ponerles un ejemplo ya. Bueno, el banco más grande del Perú es BCP, ¿ya? Pero no es que su portafolio de derivados sea muy grande. A pesar de eso, porque tiene opciones, tiene currency options, tiene swaps, IRS, cross, currency swaps, y forwards. Sí, un montón de forwards. USD Pen y USD Pen US, otras monedas. COPS, yenes, así. Pero para el cálculo de CVA, si mal no recuerdo, el portafolio se demoran 4 horas. 4 horas. Y solamente usan, me parece, 1.200 escenarios. Imagínense qué pasaría si le ponen directamente, ¿no? Dice, pero hay que ponerle 1.000.000, 100.000, 10.000. Así con 1.200 se demora 4 horas, probablemente con 10.000 o 100.000 esa vaina no sale. No sale para la fecha en la que se quiere. Porque se corta en un día, porque esta información hay que enviársela a la superintendencia. Se corta en un día, del BCR. Y en la noche tiene que correr, ¿no? Hay que hacer el Monte Carlo para poder obtener el CBA. No se llega. Entonces, en esas circunstancias, ¿no? Uno tiene que sopesar, ¿no? El trade-off entre uso más muestra y mejora la calidad, o uso menos muestra y empeora la calidad. Entonces, en ese contexto es que salta esto de aquí que hemos revisado, ¿no? Porque de alguna manera te puede decir, ok, ya, en lugar de estar poniendo números, ¿no?, de muestras de manera arbitraria, vas a tomar un criterio razonable en el cual tú dices, ok, yo me siento, tengo cierta confianza si es que el error no excede, no sé, el 1% del portafolio. O 2% del portafolio, dependiendo pues del problema en cuestión. Y de acuerdo con eso ya haces tu simulación.
Ok, profe, y para motivos de evaluación para el curso, ahí se tiene que explicar si tenemos que controlar por los errores o de simplemente corremos como que una regresión con muchos valores, ¿no?
Sí, aquí vamos a hacer. O sea, depende de la pregunta, ¿no? Depende de la pregunta. Porque te voy a decir, oye, mira, y acá no hemos fijado porque esto puede cambiar inclusive con. Ah, sí. Sí. 600. Depende de la pregunta que tengan enfrente, ¿no? Usualmente no lo hago, porque los problemas son bastante simples, ¿no? A menos que se me ocurra, así como por pregunta de un alumno en el ciclo 2022-1, tener un problema de portafolio en el cual sí, pues el ejercicio no va a correr si es que ustedes no fijan antes cuánto es el sample size. Pero igual no hay problema porque, digamos, una vez que ustedes fijan el sample size, pueden saber cuánto vale. Hasta, que era más o menos esto, ¿eh? El error.
Profe, ¿ese valor no debería ser menor al epsilon? ¿O no?
O sea, en realidad lo que debe ser menor al epsilon es el verdadero valor versus la diferencia entre el verdadero valor y el valor estimado. Y eso con cierta probabilidad, ¿no? Podría pasar que en algunos casos exceda. Por eso fijas esta probabilidad. Se podría ser que en algún caso esté por encima. Si somos 20 aquí, quizás uno tiene el error por encima. porque está al 5%.
Ahí lo que están viendo es qué tanta calidad tiene ese
Claro,
estimador,
este es
¿no?
claro, exacto. Esta es la calidad del estimador, digamos. Una vez fijado N, es lo que decíamos en la segunda pregunta. Una vez que ya fijé N aquí, ¿cuál es la calidad de mi estimador? Es esta de acá.
Ok, claro, perfecto. Eso tiene una interpretación, o sea, podemos afirmar de que es un buen estimador porque está cerca a cero o no,
Sí,
no
claro.
podemos decir.
Es como dices. Es un buen estimador porque está cerca de cero, por lo menos o sea, en la medida que sea lo más angosto, ¿no?, posible el intervalo de confianza, lo que está diciendo es que la probabilidad de que esté allí es más alta, ¿no? O mejor dicho, si la probabilidad ya la fijaste, lo que está haciendo es que simplemente no haya mucho espacio para moverse para el verdadero valor, ¿no? En algunas circunstancias podría estar fuera, ¿no? Pero bueno, es menos probable. Bueno, a ver, voy a compartir esto. Ya está. Okay, that is the two-stage procedure. We have learned how to do the two-stage procedure, and there is a sequential procedure, okay? In the sequential procedure, you will generate samples. So instead of pre-computing n like this, you will generate samples until this happens. So the algorithm for this sequential procedure is as follows. First, you set a check, an n, then you run a while loop where the while will check this check. Then you generate these guys, estimate theta hat, sigma hat, and then you will check that the size of the sample should be greater than p, and if this size is greater than the sample of the pilot simulation, and this guy is less than epsilon, you will turn this check to 1. If this doesn't happen, you will increase the size of m by 1 and continue the while loop. So the while loop will stop when this is true. When you get out from the while loop, then you compute the confidence interval using the last values, the last estimators of theta and sigma. And that's it. That is the sequential procedure. Do it with Gonzalo. Questions so far about the run length control?
Profe, ¿podría explicar de nuevo, porfas,
ese código que, o sea, que está explicando en el PPT, y luego también cómo se podría computar y vimos el absoluto por no relativo, más o menos una idea de cómo podemos computar el relativo.
Okay, check the relative. This is for the absolute. Okay. Relative. Error. Okay. For the relative error, you just need to set n using this formula. So it's the same one, but in the denominator, you have to put also theta square. Here you put that square. The epsilon, this is 1%. Okay.
Ok, entonces igual que como en el otro hicimos, como no sabemos el verdadero valor ni de teta ni de la varianza, hacemos como el estimado en el pilot simulation
You use the
y
pilot
ya agarramos el n,
estimators.
¿no?
That's it,
Claro.
as you said it.
Ah, ya, perfecto.
Two-stage procedure, relative error control. Finally. Okay. In the sequential procedure, you need a while loop because you will check always this. Okay, for the absolute error, you need to make sure that this guy is less than epsilon. If this doesn't happen, you continue with the loop. See this. Also, you put another condition that the size should be greater than some p-value. Pilot size simulation, let's say 100. You can put it here. You can start from p.
Profe, pero cualquiera de las opciones son válidas, ¿no? O sea, si utilizo el anterior, utilizo este, igual sería válido, ¿no?
Sí.
Ya, perfecto. Gracias.
¿Alguien más? Preguntitas. Determinar. ¿Qué es esto? Simulando un geometric Brownian motion. ¿Okay? Okay. ¿Ustedes recuerdan Black-Scholes? Black-Scholes, Merton. Claro. Ya vamos a ver. Black-Scholes model. According to Black-Scholes, Merton, the stock price follows a geometric Brownian motion, which means that the change in the stock price value of this follows this dynamic. Right. This is the risk-free rate. Is the stock price, the spot stock price value at time t. This is the volatility of the return stock. And this guy is known as the Brownian motion. You know that the Brownian motion distributes as a normal with mean zero and variance t. So this is equivalent to, right? Where the distributes standard normal. And our friends solve this stochastic differential equation, okay? So when you solve this stochastic differential equation, you get this. Minus times t1 minus t0 plus sigma square root of 1 minus t0 times so that is the solution of the Black-Scholes stochastic differential equation. Okay. So if you set t0 to 0, then t1 to t, you get something like this. 1/2 sigma square times t plus sigma square root of t times. And that is what we have in our set of slides. Okay, you see? And instead of w, the Brownian motion, you put a square root of t times z. But using the general solution, you can simulate random variates from this distribution, the geometric Brownian motion distribution. So if you want to simulate a random path from from the geometric Brownian motion, you just need to first set a sequence of indices and set the spot price of the stock for today, then generate these guys, standard normal random variates, and use this equation. So you will construct a sequence or a path trajectory for the stock price starting from T0. So first, when you put J1, so S of T1 will be S of T0 times exponential of this. Then once you have T S of T1, you can compute S of T2 because S of Tj depends on S of Tj minus 1. This is recursive. Now let's see how can we do this in R. Look at this. Geometric Brownian motion. First, let's say 5 sigma 30. Where do we need? S0. Let's define a sequence of time indices. Sequence. This is my sequence of indices. Okay, that is the first step. Then we set this guy. Okay, then we generate our norm. How many? Okay, that will be the size of length of t minus 1. And step 3 set as, okay, here we need to use a for loop for j in predefined as numeric and s of j will be s of j minus 1 multiplied by exponential of r minus 0.5 times sigma s squared times dj minus dj minus 1 plus sigma times a square root of dj times d. That's it. Finally, we plot s type. Now you need to cross your fingers. Yes.
Profe, creo que es el índice porque parece S de J, pero en for comienza con I. Ah, no es el mismo, perdón.
Profe.
Lo llamo.
Debería empezar en el 2 porque le tienes que asignar el primer valor el 100.
Oh, tienes toda la razón. Gracias. José Enrique. Sí. You see? Now let's make it that is the trajectory of the value of some stock according to Black-Scholes in Humberto. Okay. That's how you can simulate the whole path. I will share this with you. You know how to simulate the stock price. Geometric Brownian motion. Preguntitas. Echen un vistazo a ese código. ¿Me parece? Son 9:27. Para no quitarles más tiempo. Si hay algo que no comprenden, lo vemos la próxima clase.
Chao, profe, gracias.
Listo, Ania, cuídate.
Gracias, profe.